A couple more examples of evaluating these definite integrals using a U substitution. Sine 2x cos 2x dx from pi fourths to pi thirds. A good guess would be u equals 2x for the substitution, but the derivative du only gives us 2 dx, and unfortunately, that doesn't necessarily help us to either get rid of the sine or the cosine function in terms of u. Right? So, but this is pretty problematic of integration in general, is that we try something and it doesn't work. So then we're just going to have to try something else. Another substitution possible for this could be sine of 2x. And the reason we picked that is because we know the derivative is going to give us something close to cos 2x dx, which is nice. But remember, there's a chain rule from our derivative. So this is going to be 2 cos 2x dx for our derivative. We don't like the 2 because we don't have a 2 anywhere as a coefficient. So our du halves is going to be equal to 2, I'm sorry, just regular cos 2x dx. All right, so now we can go ahead and substitute. This is our du, and this is our u. We're going to use our dummy variables instead of pi fourths to pi thirds, a to b, u du over 2. All right, so this was our du over 2 because that was our cos 2x. We can factor out the 1/2. So we have 1/2 integral a to b u du, which is the same as 1/2 u square over 2 from a to b. And now we can go ahead and back substitute for a and b as well as u. And so this is what we end up with. We end up with 1/4. Remember that u was sine of 2x squared. And then we go from pi fourths to pi thirds. We substitute using our fundamental theorem of calculus. So we get 1/4 sine of 2 pi thirds squared minus 1/4 sine of 2 pi fourths. All right, so we're substituting, we're multiplying by 2. So this is 2 pi fourths square. All right, now we know that 2 pi fourths is the same thing as pi halves. All right, so that's just going to simplify really nicely into pi halves. All right, and then what we can do is we can just go ahead and evaluate the trig functions. Right, now to evaluate those, we should probably go back to our unit circle. And on our unit circle, we're looking for 2 angles. Okay, so right here, this is one of the angles at pi halves, and we know at pi halves the coordinate is 0, 1. And then we have 2 pi thirds, which is right about here, which is going to be negative √3 over 2, comma 1/2. Okay, or the other way around, excuse me. It's going to be negative 1/2 and our √3 over 2. All right. And remembering that the cosine is the y coordinate. So these are the values that we're going to use. Okay, so this is our 2 pi thirds, and this is our pi halves right here from our angles. Okay, remember we just go around from standard position here to get to pi halves, and we do the same thing here. All right. It may be beneficial to also have a unit circle so that way you can go through and remember these. Right. So we're going to substitute. Okay, we know that 2 pi thirds is going to be our √3 over 2. And then over here, we have sine of pi halves, which is going to be 1. When we square this out, that just becomes 3/4. So we get 1/4 times 3/4 minus 1/4 times 1, right? Or 3/16 minus 4/16 if we were to go through and get a common denominator out of this. All right. And then at this point, that just becomes negative 1/16. So this one's not too bad, okay? But it's a little bit difficult at the beginning to try to guess which is going to be the correct substitution. One more example with some trigonometry in it. And this one's going to be an inverse trig function. All right, so we have our arcsine square root 1 minus x squared dx, all right? And the bounds are root 2 over 2 to root 3 over 2. So again, this is a tricky one because we need to somehow figure out a substitution. It may be beneficial to think of the integral as this. So root 2 over 2, root 3 over 2. And I'm just going to split this off. So I'm going to write this as 1 over 1 minus x squared, square root, times arc sine of x dx. If we let u be equal to the arc sine function, the arc sine x, the derivative is 1 over the square root of 1 minus x squared dx, which is precisely what we need to be able to substitute back in for dx. So this is our u, and then these two are going to be our du. Using the dummy variables, a to b, u, again, is going to be your arc sine of x, and then du is going to be the square root of 1 over x squared dx. We know that the antiderivative, u squared over 2 from a to b, back substituting, we know that u is arc sine of x. So this is going to be arc sine of x squared divided by 2, root 2 over 2 to root 3 over 2. Right. We're going to back substitute for x by using our fundamental theorem of calculus. So we're going to get arc sine of square root of 3 over 2 quantity square over 2 minus arc sine of root 2 over 2 square over 2. All right, so again, it's helpful for us to have our unit circle, all right, to try to evaluate this. And what we're looking for is we're looking for the angle that makes this, that gives us the sine of some sort of theta. It gives us root 3 over 2, and sine of some sort of theta gives us root 2 over 2. And so in our first quadrant, okay, this is what our unit circle looks like, all right? And so we have these angles, okay? So this would be our angle of pi 6, and this would be our angle pi fourths, this would be our angle pi thirds, this would be our angle pi halves, all right, at these points, all right? And by the way, those aren't the points, those are just the angles inside. So this is really like our pi 6 right here, but I'm just trying to give these to you just to remind you, just in case it's been a little while since you looked at the unit circle, okay? So this one's going to be our pi fourths and our pi thirds, and then this one's our pi halves. All right, so the coordinates pairs, all right, and this is 0, not that it matters too much, but this is going to be the point 1, 0, and then this is going to be the point 1/2 root 3 over 2. This is the point root 2 over 2, root 2 over 2, and then this is going to be the point root 3 over 2, 1/2. Okay. Or sorry, those are backwards. I apologize. So this should be root 3 over 2, comma 1/2, right? And then this is still root 2 over 2, all right? And then over here, this one's going to be 1/2, comma root 3 over 2. And then finally right here, this is the point 1 or 0, 1. All right. So what we're trying to do is, remember, the sine is the y coordinate. So we're just looking at all the y coordinates, all right? And so we notice that we have a root 3 over 2 at pi thirds. So this is just going to turn into pi thirds squared over 2, all right, for the arc sine. And then we notice that we get a root 2 over 2 at pi fourths. So this is just going to turn into pi fourths. Now we square those out, all right? Let me erase this just so we have some room to kind of work with, all right? Because we are going to have to do a few common denominators and that sort of stuff. Shouldn't be too difficult though, because we're almost done with this. All right, so when we square everything out, we're going to get pi squared over 9 over 2. So we're going to get, this becomes pi square over 9 over 2 minus pi square over 16 over 2. Or in other words, that's going to be pi square over 18 minus pi square over 32. All right. Common denominator is probably going to be 72. All right. So maybe not 72, maybe something else. All right. So this is 9 times 2, and this is going to be 2 square, or 2 to the third. Actually, it's 2 to the fifth power. All right. So it's actually a pretty big. So 2 to the fifth. So it's actually going to be a pretty big common denominator. All right. So it's going to be 9 times 32, which is going to wind up being 288 as our denominator. All right. So, and what I did there, I just took the prime factorization. All right, this is really 3 squared. All right, and I took the highest power of each. All right, so common denominator is going to be 288. All right. And I know to go from 18 to 288, I had to multiply by 16. So it's going to be 16 pi square. And then to go to 32, I had to multiply by 9. Right. And so when we subtract that out, it should be 7 pi square over 280. All right. So a little bit tedious once we get to the ends here with the computations, but it is calculus. It's not always supposed to be easy. All right. So hopefully this helped you guys to be able to work with some of these trig integrals, especially since they have the definite integrals on them, to be able to not only evaluate by doing a U substitution, but also by being able to plug in the bounds for this.